Well, hello, ladies and gentlemen. We are going to be spending the lecture today going over two examples for using the energy balance. So that's the topics that we've been dealing with for the last couple of weeks here, or last week. So we're just going to spend the day doing a couple of examples. So what we have here is we have air in a rigid insulated container. So we have air in a rigid insulated container or tank. Insulated, rigid container or tank. The volume of the tank is 2 cubic meters. The temperature, initial temperature T1 is 293 degrees Kelvin. Initial pressure is 200 kPa. So this tank of air originally starts with a certain temperature and pressure, and then we do some shaft work with a propeller inside of the tank. And the amount of work that we do on the system is 710 kilojoules. So 710 kilojoules of shaft work on the system, okay? So what are we supposed to find? Well, we're doing work on the air, so presumably it's going to heat up. So let's find the final temperature T2, and let's do it using two different methods. The easy method, which is assuming constant specific heat and using the property relationships that we developed in the previous lecture. And then we'll assume variable specific heat and use the air tables, which contain internal energy and enthalpy as a function of temperature. So we'll initially do it assuming constant specific heat. The value for specific heat may be evaluated at room temperature, who knows? And then we're going to find the actual true temperature, T2, not the approximate temperature for constant specific heat, but the true temperature using air tables in the back of your notes, okay? All right, so let's get started here. Let's find the final temperature. Oops. Okay, so analysis. Well, our system is going to be the air in the tank. So here's our system, our control volume. We're also told that it's an insulated tank, so let's put some crosshatch around here indicating that this is an insulated tank. Insulated tank, okay? So I want to find the final temperature. Well, there are a couple of different ways to do this. Well, there are a couple of different ideas. One is you could simply use the ideal gas law. Somebody might say, okay, let's use the ideal gas law to find T2. So P2 V2 is equal to MRT2. So I could solve for T2. Let's see here. We have pressure 2, volume 2 over MR, where R is the gas constant for air. Now I have V2. This is just equal to the volume. I've got that. The mass I could probably get because I have the initial pressure, temperature, and volume. So I could get the mass. I have to calculate it, but I can get it. The only problem is I don't have P2. It's not given in the problem. I don't have P2. There's nothing I can do. So this isn't going to work. This isn't going to work. What's another way we could do it? If I have the internal energy at state 2, then I could go, let's say, to a table somewhere, an air table, and back out the temperature T2. So if I have U2, I can get, in theory, T2. So how do I get internal energy at state 2? Well, let's write the energy balance. E balance. Let's write the E balance here. Let's see here. This is a closed system. We're surrounding the mass of air. There's no mass crossing the system boundary. No mass crossing the system boundary, so it's a closed system. So let me write the closed system energy balance. Which one? Rate-based, per unit mass, overall process, differential process. Well, we are given the shaft work, the total shaft work over the process. So we are given the overall shaft work over the process 1 to 2. So why don't we write the energy balance for an overall process? So we have Q 1 to 2 minus W 1 to 2 is equal to delta E 1 to 2. Change in total energy. By the way, the change in total energy is equal to the change in internal plus the change in kinetic plus the change in potential energy over the process 1 to 2. Well, let's whittle this equation down and see what we get. Let's start with the left-hand side. Cause, effect. Cause on the left, effect on the right. Let's see, what's the heat transfer from state 1 to state 2? Well, we're told it's an insulated tank. Whoops. Insulated tank. Insulated means no heat transfer. There's some insulation around the tank. So we can neglect heat transfer. Q 1 to 2 equals 0. Insulated. Insulated. Okay, so that gets rid of the heat transfer term. Insulated. No heat transfer. What about the work term? Well, remember there are 3 different kinds of work. Shaft work, well, there's actually 4. We haven't talked about the 4th one yet. The ones we know about are shaft work, electric work, and boundary work. Now, I don't see any wires in here. All I see is a shaft with a propeller, and it's a rigid tank. It's a rigid tank. If it's rigid, it means there's no change in volume. It's an isochoric process. So W bound 1 to 2 equals 0 because it's isochoric. And I don't see any wires in there, so I'm also going to write W electric 1 to 2 equals 0. Okay, no electric work, no boundary work. All that's left is shaft work. So this W 1 to 2 is actually W shaft 1 to 2. W shaft 1 to 2. Okay? Now let's tackle the right-hand side, the change in energy. We don't know anything about the container in terms of its position or its velocity. There's nothing in the problem statement about it moving or accelerating. So I'm going to write it down in the assumptions here, but I'm going to neglect changes in kinetic and potential energy. I'm going to assume those away. Okay? So I'm going to write that down in the assumptions. Delta PE equals delta KE, and they're both equal to 0, okay? So we're going to assume away changes in kinetic and potential energy. Okay, let's see what we got here. Minus W shaft 1 to 2 is equal to delta U. 1 to 2. Now let me write that in terms of change in specific internal energy. So mass of the air times delta little u from 1 to 2. Okay? Now this is where I'm going to stop. I'm going to call this equation number 1. Okay? I'm going to call that equation number 1. I'm going to stop right here because This is where the problem branches off depending on how we evaluate the change in internal energy, either using tables or using specific heats, okay? So I'm gonna stop right here. It's gonna stop right here. We're just gonna leave that equation where it is. So let's calculate T2 for part A. So A, and A, if you look here at the given, we're going to assume constant specific heats evaluated at 300 degrees Kelvin to get our final temperature. Constant CP and CV evaluated at 300 degrees Kelvin. That's how we're going to solve for T2 for part A. So the problem splits up at this point. Okay, so let's recall from the property relationship, du is equal to CV dt. That's a property relationship that we derived last time. In other words, delta U is equal to the integral of CV dt, which is approximately equal to CV evaluated at some temperature times delta T. So I'm going to assume CV is constant. I'm going to pull it out of the integral. So I'm going to evaluate it at some temperature. It's going to be a constant. Pull it out of the integral, and I get CV delta T. CV evaluated at some temperature, okay? In our case, we're going to evaluate it at 300 degrees Kelvin. That's 27 degrees C, so that's room temperature approximately, okay? Okay, so let's substitute this. So this is delta U from state 1 to state 2. So this is integral CV dt from T1 to T2, which is approximately CV evaluated at some temperature. I'm saying 300 degrees Kelvin times delta T from state 1 to state 2. Okay, that's using the property relationship, constant specific heat, pull it out of the integral. Okay, let me write our equation here. Negative W shaft is equal to M air delta U from state 1 to state 2, which is equal to M air, it's actually approximately equal, CV evaluated at 300 degrees Kelvin, delta T from 1 to 2, and that's equal to the mass of the air, CV evaluated at 300 degrees Kelvin. Delta T is T2 minus T1. T2 minus T1, that's delta T over the process. Okay, I'm going to solve this equation for T2. Let's solve it for T2. So this implies, T2 is equal to minus W shaft 1 to 2 divided by MCV evaluated at 300 degrees Kelvin plus T1. Okay, so I divided both sides of the equation by M air CV, and then I took the T1 over on the other side of the equation and I flipped the equation. So T2 is equal to minus W shaft over MCV plus T1. Now, let me get this looking a little bit better here. That looks better, okay. If you want to put an approximately equal here, that's fine too, okay? Because we're assuming constant specific heat. Let's see here, I have W shaft. I have T1. T1 is 293 degrees Kelvin. I don't have the mass of the air, and I don't have the specific heat. Let's see if we can find out what these are. First of all, let's calculate the specific heat evaluated at 300 degrees Kelvin. Let's see here, share screen. All right, so here's table B10, specific heats, ideal gas, CV, 7.18 kilojoule per kilogram degree in Kelvin, 7.18 kilojoule per kilogram degree in Kelvin. So CV evaluated at 300 degrees Kelvin is 0.718 kilojoule per kilogram degree in Kelvin, and that's from table B10, okay? By the way, I haven't written it, and I think I should write it right now. I'm assuming ideal gas behavior. IGB valid. Okay. So now we got the specific heat. That's done. Let's calculate the mass for the air. M air, and this is using the ideal gas law, is equal to P1 V1 over RT1. Okay? I just evaluated the ideal gas law at state 1. Let's see here. The pressure is 200 kPa. The volume is 2 cubic meters. The gas constant for air, 8.314 divided by the molecular weight for air. Let's see here. Again, let's look up the molecular weight for air. .97. 28.97. And temperature T1 is 293 degrees Kelvin, okay? The units here, everything's in kilo. So the kilos will all cancel out, and we should get kilograms for our unit. I'm not going to go through and do the unit here. Well, all right. So this will have units of kilojoule per kilogram degree in Kelvin. The kilojoule and the kilopascal will cancel out. So we should have kilograms when we do this. Let's see here. 200 times 2 divided by 8.314 divide by 293 times 28.97. And I get 4.76 kilograms. That's my mass of air, 4.76. Okay? All right, so I got everything. I got the mass now. Let's see here. Let's plug in. W shaft. Remember the energy balance. In the energy balance, W is by the system. If the system does work, work is positive in the energy balance. We're told that the shaft is doing work on the system. 710 kilojoules on the system. So the numerical value that we're going to plug into the energy balance is going to be negative. So it's going to be negative 710 kilojoules on the system. And then I have the mass, which is 4.76 kilograms. And then the specific heat, 0.718 kilojoule per kilogram degree Kelvin. And then I have T1, which is 293 degrees Kelvin. Okay, let's crank that out. Let's crank that out. Let's see here. 710. Be a little careful here. Yeah, the kilojoules are going to cancel out. Just check the unit here. Kilograms cancel out, and I'll get degree Kelvin there. So divide by 4.76 times 0.718 plus 293. And I get 500.7 degrees Kelvin. So T2, and this is for part A, constant specific heat, 500.7 degrees Kelvin. So for part A, 507 degrees Kelvin. Now, we were able to do this problem without looking at the air tables, giving internal energy and enthalpy. We use specific heat, constant specific heat, assumed a constant specific heat value at room temperature to estimate T2. Let's see how much an error, let's try to eyeball how much error there is associated with assuming constant specific heat. Let's just eyeball it. So let's look at CV here for air. So let's see here. We end up at 500 degrees Kelvin. So maybe 400 degrees. We start off at about 300 degrees. We end up at 500. The average specific heat is going to be around 0.726 instead of 0.718. 400 degrees is the average temperature over the process. 500 plus approximately 300, so that's 400 degrees. So that represents about a % variation or error between the true average specific heat, 0.726, and 0.718, which is evaluated at room temperature. So we expect our T2 to be incorrect by about a % or so. Not bad, not bad for engineering work. Not bad for engineering work. Let's calculate the exact temperature T2. Let's calculate the exact temperature. We're going to use tables to do this. We're going to use the air tables. So I'm going to go back to my equation here. W shaft 1 to 2 is equal to M delta U 1 to 2, which is equal to M U2 minus U1. Now let me get U2, and then I will go calculate the temperature, okay? So this means U2 is equal to minus W shaft divided by the mass of the air plus U1. Now, what's U1? First, let's calculate U1. What's internal energy at state 1? Let's see here. U1 is U evaluated at T equals 293 degrees Kelvin. 293 degrees Kelvin. Let's see here. 200. So we got the air tables here, internal energy, enthalpy, 290, 300. So internal energy is somewhere 293 degrees Kelvin. It's somewhere between 206 and 214. 206 and 214 kilojoules per kilogram degree in Kelvin. So let's see here. We do a little bit of interpolation here. I guess we should go through and do the interpolation. All right, so let me take (293). Let me take my reference here, my base temperature and internal energy at 290, corresponding to 20691. So 290 plus 206, 9.1 kilojoules. I'm sorry, 206.91, and then the upper value is 214 at 300. 214 at 300. Okay, let me take the screen off here so we can get back. Let's see, 214.07, 206.91. Okay. Oh, I wasn't sharing this. So 293, this is going to be my base value for temperature and specific internal energy. And so I'm going to do an interpolation between 290 and 300 degrees Kelvin. Okay, so 290 plus delta temperature over delta U, 206. I guess I'm gonna, I guess I'll leave the 9 here. And let's see here, I'm 293 minus 290 degrees Kelvin, okay? I'm sorry. U2. Oh, let's see here. Am I doing? I'm not. I need to do the opposite here. Yeah. (300) minus 290 degrees Kelvin. And then I have, got to look them up again. I should have done this beforehand. 214.07 and 206.91. 214, 206.9. And this has units of kilojoule per kilogram. And then I got 293 minus 290 degrees Kelvin. The Kelvins cancel out. I need my base. Doing this wrong. I need my base 206.9 kilojoules per kilogram. I seem to be interpolating temperature, not internal energy. Okay, that should work. Okay, let's see what we have here. 206.9 plus 214 minus 206.9 divided by 10. And then I'm going to multiply this by 3. And I get 209.0 kilojoules per kilogram. So U1 is 209 kilojoules per kilogram. Check. Okay, let's calculate U2. W shaft, negative 710. And then I got the mass. Ooh, what was the mass again? It's like 4.76 kilograms. Okay. And then I have plus 209 kilojoules per kilogram. Okay, 710 divide by 4.76 plus 209, and that gives me 358. 358 kilojoules per kilogram. 358 kilojoules per kilogram. Now, T2 is T evaluated for an internal energy, U2. T2 is T at U2, and U2 is 358 kilojoule per kilogram. Now, how might we figure that out? So we have an internal energy at state 2, 358 kilojoules per kilogram. So let's find 358. It's between 352 and 359. So it's closer to 500 than it is to 490. Okay, closer to 500 than it is to 490. So we can do some interpolation between these two data points. Interpolation between the two data points, and I find a temperature of 498.27 degrees Kelvin. 498 point, let's see here, 0.27, or 3 if you like. And this is by interpolation. Interpolation from tables. 498 degrees. We got 500 degrees using constant specific heats, 498 degrees using variable specific heats, i.e. this is the true temperature in the container at state 2. Actual temp, actual temperature. Actual temperature using the true specific heat, using the true internal energies, variable specific heat, not constant specific heat. Constant specific heat calculations are approximations. We got pretty good, 500 for constant specific heat, 498 for variable. If we would have chosen a specific heat evaluated at 400 degrees Kelvin instead of 300, we would have gotten a value probably closer to this, okay? A lot closer to 498. All right, ladies and gentlemen, let's take a pause here and we'll do one more problem.